Good morning, sir.
Good morning. My screen is visible.
Yes, sir.
Okay. Okay, so let us start with today's lecture. Last time we derived expression or we derived equation of motion, or you can say equation for electromagnetic equation of motion of electromagnetic waves, wave equation for electric field component as well as magnetic field component of electromagnetic wave. And this we did specially for vacuum for free space. When electromagnetic wave travels through free space, then these are the wave equations. What is special about these wave equations? You can see these are partial differential equations. You understand now what are partial differential equations and what are ordinary differential equations. So partial derivative is involved because E is a function of partially depends on, you can say, space coordinates, and it also depends on time. So it is function of x, y, z. With that three space coordinates, it also depends on time t. So this is partial derivative with respect to space coordinates, and this is partial derivative of electric field with respect to time. And these are permittivity and permeability of free space, and we equated it with the general wave equation. That is, this is general wave equation for any wave, and this is what it is, reciprocal of square of velocity of this wave. So when we equate this standard wave equation with our wave, or with wave equation for EM waves, we see that velocity of waves, electromagnetic waves in free space is under root 1 divided by under root mu naught epsilon naught. And these are standard constants, epsilon naught, mu naught, and we put values for these, then we see that this is 2.99 into 10 raised to the power 8 meter per second, which is what? Which is speed of light through free space. Today, before starting with, or we'll be writing wave equation, similar type of wave equations for both electric and magnetic components of electromagnetic wave. But when wave is traveling, it is not in free space, it is not in vacuum, it is traveling through a medium with defined properties. Some properties of that medium will be known to us, and depending on that, we'll see how electromagnetic wave travels through that medium. Okay, so this is helping us. This new form of electromagnetic waves are helping us in driving these wave equations and in understanding how electromagnetic wave behaves with medium or with different material medium, or how electromagnetic wave it travels. Okay, so here our conclusion is that whenever electromagnetic waves, they travel through free space, through vacuum, they travel with this speed. E and B components, you can prove number of things from these wave equations. That E and B fields are perpendicular to each other. There is no phase difference between E and B. How their magnitudes or amplitudes are related. E and B field, they have a special relation between their amplitudes, and we can drive number of things. Okay, that is part of exercise or a part of assignment for you. And today we'll discuss propagation of these electromagnetic waves in some other medium. And before doing that, let us understand one more basic fundamental property, that is equation of continuity. And what is this equation of continuity? It is about conservation of charge. You have seen that charge is conserved. Conservation of charge means that in an isolated system, total charge remains same, remains constant, it is conserved. And we can write that equation, that mathematical expression for this conservation of charge, yeah, equation of continuity. We write this in the form of equation of continuity. Again, this is differential in the form of differential form or differential equation, which is also helpful for us in understanding when we will be doing higher propagation of electromagnetic wave and other. So we have, suppose this is our conductor through which charge is flowing. This is my conductor. Charge is flowing, current is flowing, or charge is flowing due to which there is current in this conductor. Let me choose arbitrary volume part of this conductor. This is some arbitrary part of this conductor having volume, small volume of this part is what it is dV. And if no current is flowing, I'm saying that initially there is no current or no charge. We can say that this is what this is, volume charge density. Volume charge density. And we can write charge within this region or within this volume V is dq, and this charge dq is product of volume charge density rho and volume dV. This is dq. Okay, so when we apply some electric field, charge, it starts flowing, it flows out of this volume, and then we can write what? We can write expression for I, or through this closed surface. So we write I is current, which is minus d by dt of q. Why am I'm writing minus sign here? Because charge is flowing out, and it is decreasing what? It is decreasing charge density. Okay, when it flows out of this region, small volume, or through out of this closed surface, then this is written as minus d by dt of q. Or I can write it is minus d by dt of charge inside this is given by density. Rho is volume charge density of this region, and dV. Or I can write this as this is integral of d by dt of rho dV. Okay, and one more thing, I know that the charge is flowing out of this closed surface, and if charge density is sigma, sorry, charge density is J, that is not charge density, current density is J, that is current flowing out of this per unit area, then I can write it as J dot ds. We have written this earlier also. This is small current di, and closed line integral of this is what it is, total current flowing out of this closed surface S, which is equals to what? Which is equals to, as I have written, negative of d by dt of q. So we get what? We get this equation. This is what? This is from this. I know that charge, due to flow of charge, current is there. And if charge is flowing out of this defined volume, then we say that it is minus d by dt of q. Q will decrease with the flow, and that contributes to current. And that can be written in integral form using definition of current density and rho, that is volume charge density, and then we write it like this. Again, as we did in case of when we derived Maxwell equations from standard laws of physics, we used either Gauss divergence theorem was used or Stokes theorem was used. We can see on this left hand side here, we have surface integral, and it is closed surface integral of J. J is our field, vector field. Then I can write that this can be using Gauss divergence theorem. I use Gauss divergence theorem to write this in volume integral form. So I can write that it is what? It is volume integral of divergence of vector field, that is J in this case. So it is volume integral of divergence of J, which is equals to volume integral of uh, d by dt of rho with negative sign dv. I can equate integrants as we know that this is arbitrary, volume is arbitrary here. So I equate integrants on both the sides. So I can write that divergence of J is negative of d by dt of rho. Or if I shift it to this side, I can write this is equals to 0. And in case of steady state, when rho is constant, no change in charge, volume charge density, that is steady current is flowing, steady state case, then we can see that this will be equal to no change in rho, means d by dt of rho is 0, then divergence of J equals to 0 is also this is what this is conservation of charge, this equation, because divergence of J is equals to negative of d by dt of rho. Whenever there is divergence of current, okay, divergence outflow, then there is through any volume, v volume, that will decrease the charge density, volume charge density. So it is minus, so that is giving you what charge is flowing out, and you reason for change in current density is this. हेलो, परम जी क्लास में बात में करते हैं. So this is what this is. This is when there is steady case, you know, whatever is flowing in, that is flowing out. Then we say that there is no change in rho, and then this is what it is equals to divergence of J is what it is 0. So this is equation, another equation we added, and so we can write, we have four Maxwell equations. Divergence of E equals to equals to rho divided by epsilon naught for free space, or otherwise it is only epsilon. So I'm writing for free space it is epsilon naught, means this gives you what, that electric field is the reason for electric field, or electric field is due to what, it is due to rho, that is charge, volume charge density, and divergence of magnetic field is 0. This means, or physical meaning, physical significance is what, that monopole does not exist. So it is what field is due to dipole, and flux due to dipole is what it is 0. Then another equation is about electric field, how electric field, reason for this electric field is rate of change of magnetic field. So electric field is not only due to some charge density or charge distribution, it is also due to what, it is due to rate of change of magnetic field. Or for free space, sometimes we write it mu naught times d by dt of h. Okay, so with negative sign, and then we write the fourth law, which is about curl of magnetic field H. This is J, that is conduction current density. This is C, conduction current density, plus this is epsilon naught times d by dt of E, that is electric field. So here, this is current, sorry, magnetic field is due to what, it is due to conduction current, and it is also due to what, it is due to, it can also be produced due to changing electric field. So these are the four equations. They give you origin of electric field and origin of magnetic field. So here origin of electric field is what it is charge. Here it is monopole. Here it is electric field is due to changing magnetic field, and here magnetic field is due to conduction current as well as due to changing electric field. So this is displacement current, and this is what this is conduction current. Okay, so one more, and this is not part of this, but I'm saying that we have one more relation, that is this in case of current which is flowing, and in case of steady state current is flowing, but inward is equals to outward. Then we say that this is our equation of continuity. Okay, so now we want to write wave equation for electromagnetic wave which is propagating in some medium whose properties are given to us, and medium is what it is, conducting medium. So we'll be following the same steps as we did earlier to write wave equation for electromagnetic waves in free space. So we'll be writing wave equation, we will be writing Maxwell equations or the four Maxwell equations for this conducting medium. And then using those Maxwell equations and doing some mathematics, we can write wave equation for E, as well as separately we write wave equation for both the components of electromagnetic wave, that is E component as well as B component, or you can say electric field component and magnetic field component of electromagnetic wave. So before doing that, let us understand what is a conducting medium. If medium is a conducting medium, how it is different from a free space? Now it is not a free space, it is not a vacuum. So as medium is conducting, so let us try to write wave equation, Maxwell equations for this conducting medium. Okay, let us say conducting medium means what? It is rho is zero, volume charge density is zero. Why volume charge density is zero? Because it is medium is conducting, charge inside this will it will be having more potential here. It will be closer. अगर ये सारे positive charges they are at the center, so they are very close to each other. So there is repulsion, electrostatic repulsion, and they will move away because it is medium is conducting. It is not non-conducting medium or dielectric medium. Charge easily flows through this medium, so it goes to this. So surface पे charge reside करेगा. So we can surface charge density is non-zero. Okay, but volume charge density is what it is, zero. So first thing is that surface charge density is, volume charge density is zero. So we can write first equation that divergence of electric field E it is due to what? It is due to this volume charge. So volume charge density is zero. So this equation is what it is. It is this, that divergence of E is zero. Okay. Then as no charge is enclosed by a closed surface because it resides on the surface. This is my Maxwell's equation number one. And as this is conducting medium, so conduction current will be there. It is non-zero. And with this, displacement current is also there. It is non-zero. So, and as this is now medium, which is not a free space, so I can say that these are two more properties of this medium, having permittivity, this, and permeability mu. It's given by mu. Okay, as it is having permittivity epsilon and permeability mu, I can write two relations, that is electric field can be written as I said, that it is epsilon naught, or you can say, okay, this is, or I can write that, let me write D, that is electric displacement vector. It is epsilon naught times E plus polarization vector P as polarization vector, we'll see. So, but this I can write equals to epsilon times E. Okay, so this is a relation between electric displacement vector and E, and I can also write that B, magnetic field intensity, is equals to mu naught times, not mu naught, it is mu times H. So keeping all these relations in our mind for our medium, that is conducting medium, I can write Maxwell equations, all the four Maxwell equations. My second Maxwell equation, it remains unchanged, that divergence of magnetic field B is zero. I have third equation, which is about curl of electric field. So curl of electric field is equals to negative of, I can write here mu d by dt of H using this. And I can write Maxwell's equation number 4, that is about curl of H magnetic field. It is conduction current, non-zero, plus it is displacement current, which I write epsilon times, because it is d by dt of, it is d by dt of electric displacement vector d. So I can write it as using this, it is epsilon times d by dt of electric field E. So these are my four Maxwell equations for conducting medium. I used all the properties of conducting medium, and using those I can write Maxwell equations in this form. Now, using the same mathematics as we did earlier, we can write wave equation for E component as well as B component, but these wave equations will be different from the wave equations we saw in case of free space or vacuum. So, and then we'll see what conclusion we can draw from that difference. Now I take curl of, I started with the same steps which were followed earlier. So I take curl of equation number 3 to write wave equation for E component of electromagnetic wave. This is how we started in case of vacuum as well. So curl of equation number 3, this is my equation number 3, curl on both the sides. So curl of E, this is curl of E on right and left hand side, is equals to curl of this term, that is my negative mu times d by dt of H. I can straight away interchange the operation of two operators. I'm writing d by dt and I'm operating with curl operator on H first, and then I'll do d by dt of this. So this is what I get. I take curl on both the sides, and I can, using the formula as I said earlier, this is nothing but this is gradient of divergence of E. This can be expanded as gradient of divergence of E. So this is gradient, no dot here. So minus del square E is equals to minus mu d by dt, and I can replace this using Maxwell's equation number 4. Curl of H is sum of conduction current density plus displacement current density, which can be written as epsilon times d by dt of E. And also use Maxwell's equation number 1 to see that this is equals to 0. As this is 0, I'm left with this term and this on right hand side, and I can see I have negative sign on both the sides. I can cancel this with this. I can write del square of E is equals to mu, it is this. So I can, and one more thing, as I know that my medium is conducting, and suppose sigma is the conductivity of this medium, then I can write conductivity in terms of current density and electric field, because conductivity is defined as current density per unit electric field. So I can write this as this. So sigma, which is current density per unit electric field, is this gives you this relation. So I can use this is conduction current, this is conduction current density. So in I can write here it is sigma d by dt of electric field E. I used this relation plus operation of this on this will give you mu epsilon double derivative d square over dt square of electric field E. Okay, so I have this equation. In this equation, you see I have two double derivatives. This is double derivative with respect to time, and here I have double derivative with respect to space coordinates. And to simplify my problem, let me say this is what, or you can see this is wave equation for an electromagnetic wave, which is not restricted, or you can say unpolarized. It is moving in all possible directions. It is propagating in all possible directions. So if I write a wave equation for an electromagnetic wave, which is propagating only along positive x direction. So then I can replace this del square by d square over dx square. Direction of propagation is only x. So I write it like this. And I shift these terms to left hand side. That is minus mu sigma d by dt of electric field E minus mu epsilon double derivative of electric field with respect to time equals to 0. This is wave equation. This is wave equation for an electromagnetic wave which is traveling along x direction. It is polarized electromagnetic wave having E field, you can say, along y direction. This is E field EY, which is a function of x and t, and I have B, which is along z direction. So BZ, we can write BZ component of electromagnetic wave. It is polarized in this plane. Okay, so YZ plane. So it is a function of x and t. So I have derivative of this electric field with respect to x, with respect to time, because it is function of x and t, and this is y component of electromagnetic wave. As it is polarized, so no need to write y component. So we are writing this as wave equation for electromagnetic wave propagating through conducting medium. Okay, similarly, we'll do more analysis of this. We'll see how this is propagating and what is happening to this electromagnetic wave when it is propagating in conducting medium. But before that, let me write another wave equation for the other component of electromagnetic wave, that is H component of electromagnetic wave or B component of electromagnetic wave. So we know to find to write wave equation for H component of electromagnetic wave, we take curl of equation number 4. Okay, taking curl of equation number 4, and then again following the same steps, same procedure, we can write a wave equation for H component of electromagnetic wave. So let us see what we have. We can directly write that. This is our wave equation for E component of electromagnetic wave, and similar wave equation you can see here. Similarly, we take curl of equation number 4 and we write wave equation for H component of electromagnetic wave. So taking curl on both the sides, you see here this is curl on the left hand side, this is curl on the right hand side, and then you get this equation. This is wave equation for H component, and this is wave equation for E component of electromagnetic wave. Okay, so as I said earlier, let me choose any one and see what it means, and same will be true for the other component of electromagnetic wave. So this is one dimensional form. As I said that we simplify this, and for one dimensional case, say along x is if wave is propagating, so we can write wave equation in this form. This is now wave equation. Now it is difficult to solve partial differential equations, but what I know that how my electric field behaves. And I know that if this is what this is plane polarized electromagnetic wave, and which component of electric field is there in this plane polarized electromagnetic wave. It is y component, and direction of propagation is what it is. It is x. So I can write that wave equation. It is sinusoidal wave, and this wave this electric field component of this electromagnetic wave is given by amplitude of this electromagnetic wave, and this is exponential function of iota omega t minus kx. This is my electric field, which varies sinusoidally with time as well as with x. It is like this. This is electromagnetic wave. It is propagating in this direction. This is x direction. This is E component only. I'm not writing the other component, that is B component. This is direction is suppose y. This is z. So I'm writing EY. This is EY. Okay, so this varies with what? You can see that this EY, it varies with X as you move along this direction, that then this EY varies, and it also varies with time. Okay, and so T and X are the variables, or this is position, and this is what? This is time. K is wave number, wave vector, which is wave number, which is 2 pi divided by lambda. Lambda is wavelength of this electromagnetic wave, or E component, or both the components, they have same wavelength. Omega is angular frequency, which is 2 pi nu, angular frequency of electromagnetic wave, and this is amplitude of this electromagnetic wave. Okay, so we see that here we are assuming that amplitude is constant. Let us see what happens if we let us, because I'm interested in finding a relation between these unknowns, that is k, omega, and amplitude. How when electromagnetic wave it propagates through conducting medium. So let us see what is the relation between these parameters. So for that, my solution, this is my assumed solution, or you can say this is what I expect. I plug this solution back in my differential equation, that this is my differential equation. And I see this is my E field or solution to this equation. I'm not, or we are not able, because we do not know how to deal with partial differential equations. There is a method to deal with partial differential equations. We have to do separation of variables technique, but it is from higher mathematics. So we are writing that solution to this type of electromagnetic. If we do it by separation of variables technique, definitely we can write what we can write, this type of solution. As I said that we know solution is of this form. So it is E naught exponential function of this, that is iota omega t minus kx. Okay, k is wave number, omega is angular frequency of this electromagnetic wave. So when I plug this back here, to plug this electric field back in my differential equation, because it is solution to this differential equation, so it should satisfy this differential equation. So for that, double derivative of E with respect to x is required. We'll put that here. Derivative of electric field with respect to t, and double derivative of electric field with respect to t. So we can do that. If I differentiate this with respect to x, so it gives you what it gives you. And derivative of E with respect to x is minus iota k, and rest is same, so I can write E Okay, and if I do differentiate this one more time with respect to with respect to x, I get double derivative of e with respect to x, which is minus ik times one more time ik e. Okay, which is nothing but it is minus k square e. And I also require this, that is derivative of electric field with respect to t. So when I differentiate it with respect to t, it is I omega, and rest is what it is electric field E, because derivative of exponential function e raised to the power x, when I differentiate it with respect to x, is e raised to the power x. You all understand. So we are writing it in quickly, and this is double derivative of e with respect to time. One more time, if I differentiate this, it gives you iota omega square. So it is what it is, minus omega square e. So when I plug in these derivatives in my differential equation, so I'm plugging my solution of this differential equation back in the differential equation, so that equation is satisfied. So I get what? I get first term is this double derivative of e with respect to x. So it is minus k square e. Then I have plus mu, sorry, it is negative sign. Let me use, this is negative sign here. So it is negative this mu sigma, and derivative of e with respect to so like iota omega e minus mu epsilon, and double derivative of e with respect to t, which is negative negative cancels, so it is this is equals to 0. I can take e common, and e is not 0, as I know I have electric. So I can say that minus k square minus iota mu sigma omega plus mu sigma omega square is equals to 0. Okay, or we can invert these signs, multiplying forward by negative sign. So I can write that k square, and I can take what common? I can take this mu epsilon omega square common. So I have left with I sigma divided by omega minus 1 equals to 0. Or I'm interested in k, so my k, that is, this is small k, this is small, this is k square is equals to, I can write it as mu epsilon omega square 1 minus I sigma over omega. Epsilon is also there because I have taken this. This is epsilon, and if I take under root of this, and this is k. So wave number is what? It is under root mu permeability, epsilon permittivity of the medium, omega is, this is not property of the medium, this is property of electromagnetic wave. This is angular frequency of the electromagnetic wave which is propagating through this medium, having mu and epsilon as permittivity and permeability, or permeability and permittivity. And this is what, this is also property of the medium, it is what it is, conductivity of the medium. Okay, now what we can see that I can write, let me write this as, uh, okay, let me say that if this sigma divided by omega epsilon is very, very greater than 1, then I can neglect what? I can neglect 1 and I'll be left with this. And this means what? I'm talking about what type of medium. This is case 1. When my medium is, for my medium, this ratio, because this is conductivity of the medium, this is angular frequency of the electromagnetic wave passing through this medium, and this is epsilon, which is permittivity of the medium. So this ratio depends on what? It depends on medium as well as on the frequency of electromagnetic wave propagating through the medium. If this is very, very greater than 1, suppose we fix our electromagnetic wave of given frequency, then it depends on sigma divided by epsilon. And if it is very, very greater than 1, that means what? This ratio is greater than 1 or very, very greater than 1. So medium is conducting medium. Okay. This is what? This is conducting medium. Epsilon less, and when this numerator is big and this is small, so this will be very, very greater than 1, and numerator big, conductivity big, and this permittivity of the medium is less. So that means it is what? It is a conducting medium. And in case this ratio is very, very less than 1, then you are talking about dielectric medium. Then we are in dielectric medium. Okay, so for conducting, we are dealing with conducting. We are doing this derivation for conducting medium. So that means this ratio is what? It is very, very greater than 1. And then 1 can be neglected in comparison to this. So I can write K for this conducting medium is under root mu epsilon omega, and then it is minus I sigma divided by omega epsilon whole raised to the power 1 by 2. I can take this I term out. So let me do what? Let me take this out of this under root, and let me say if I take this out, so I have minus iota this, or I do one more thing. Let me multiply this with 2 and this as well with 2, making no change. But what I have minus 2 iota here under root. Okay, which I can write, this is 1 minus iota. Okay, you can see this. This is minus 2 iota is equals to 1 minus iota square, and 2 minus iota is, you expand this, you get 2 minus iota, so it is 1 square, and plus square of iota is minus 1, and it is minus 2 iota. This goes with this, and this is equals to this. So that means I can replace minus 2 iota whole under root by 1 minus iota. So I get two components for my wave vector. This is imaginary component and real component of wave vector. So it is what? It is 1 minus iota. This is sigma divided by 2 omega epsilon whole under root. So I can see that K can be written as alpha, okay, minus iota beta. You can identify where is alpha. If I expand this, I multiply it with this term. So it is under root mu epsilon omega sigma divided by 2. This is when I multiply it with 1 minus iota, and again you get the same term sigma divided by 2 epsilon omega whole. So alpha is what? It is this is alpha, and this is beta. This is beta, means imaginary. These are components of wave number k. This is a real component and this is imaginary component of k. Both are equal. You can see that alpha is equals to beta. Both are equal, both the components. Okay, so now we can see that I can rewrite my solution. This is my solution to this propagating electromagnetic wave. E component of this propagating electromagnetic wave is this, according to this solution when we solve this differential equation. So now my K is having real and imaginary components. So I'll be writing K as alpha minus iota beta, where beta I know what it is and what is alpha. Okay, they depend on conductivity, permeability, and omega, and permittivity as well, that is mu. So I can write this is what we said, that this is when we have dielectric medium, this ratio is very, very less than 1. And when this ratio is very, very greater than 1, that means medium is classified as conductor, as a conductor. And with this, as I said, that this ratio, this on omega, that is frequency of the electromagnetic wave, which we are making incident on the medium. So how medium will behave as a dielectric medium or as a conducting medium, that also depends on the frequency of the electromagnetic wave. So we can take very good example. This is for fresh water. We know dielectric constant, which is epsilon divided by epsilon naught, is 80, and conductivity is 10 raised to the power minus 3 mho per meter. Now, for this medium, we know these two parameters, and now depending on omega, that is the incident electromagnetic wave, if we use electromagnetic wave of this angular frequency, that is 2 pi into 10 per second, then this comes out to be, using all these values here, this for omega, this it is 2 into 10 raised to the power 4, and which is very, very greater than 1. So medium, fresh water medium for this frequency is a conducting medium. Same water, but if frequency is changed, if I use this frequency of electromagnetic wave, which is 2 pi into 10 raised to the power 10, it is bigger frequency then. So this will make this ratio less. So this is very, very less. It is 10 raised to the power minus 5. So it is very, very less than 1. So the same medium, due to change in omega, due to change in the frequency of the incident electromagnetic wave, it behaves differently now. Earlier it was conducting medium for this frequency of electromagnetic wave. Behavior of the medium was conducting, and now for this it is what it is. It is a bad conductor, or it is a dielectric medium. So this is what we said. This is components of K wave vector. So my solution will look like what? We'll be having K with alpha as real part and beta as imaginary part. So if I use these values of this value of K in my solution, that is E of electromagnetic wave, E vector of electromagnetic wave. So my wave solution looks like this. This is what it is. This is my solution. Let me put K here. K is this. So it looks like what? It looks like this. It is in place of K, I have imaginary and real components. And ये किस पे depend कर रहे हैं? This K is now in terms of what? It is in terms of properties of this medium, conducting medium. It depends on mu. It depends on depends on conductivity, sigma. Okay, so we can do what? We can now separate. We can जो आपका यहाँ पे it was, so I can take that out. If you see, I can write this exponential as e raised to the power iota minus bx times rest of the is omega t minus alpha x. So I'm separating these. Okay, I'm writing this as this, and it is E naught. So E is equals to what? It is E naught, and this exponential with this power is split it into two terms. This now you can see that this is this is what this is amplitude. This is amplitude, a real part. I've taken real part out, and this is imaginary part of exponential function, and this is real part of exponential function, and this real part of exponential function is giving amplitude. This is earlier it was E naught when it was propagating in free space, so there was no change in amplitude. Amplitude with x does not change. Amplitude remains E naught. It remains E naught every time. But now it is through conducting medium. So you see amplitude is what? It is E naught times e raised to the power minus beta x, and you can see e raised to the power minus beta x. This function decays with x. As x becomes big and big, this will decay. So that means this is attenuated wave. This is wave like big amplitude first, then it decays like this. This is how this electromagnetic wave is propagating. Yeah, E component of electromagnetic wave, amplitude of E component of electromagnetic wave is decaying like this. Is exponential decay in amplitude of the electromagnetic wave. And this beta, you know what it is. We have uh, alpha and beta both are equal, as we said in the previous slide. So, and this is absorption coefficient. If you remember right from laser, we are saying that e raised to the power minus this coefficient times x. If this coefficient is negative coefficient, so then and gain is what when e raised to the power plus some gx. This is positive, then we exponentially up intensity बढ़ता है, and this is decaying. So same is what we are saying here, that amplitude of this electromagnetic wave is decaying exponentially with distance x, with the distance or with the direction of propagation of electromagnetic wave. And in case x, this x equals to 1 by beta, distance कितना move किया electromagnetic wave ने, it is equals to 1 by beta, then you will see that amplitude will be what? E naught e raised to the power minus beta x is then equals to E naught e raised to the power, this x is 1 by beta minus 1, or it is this. Sorry, it is this. So that means x for which amplitude reduces by this factor. Okay, it becomes 1 by e of the original amplitude. So that x is what it is called skin depth of this for this medium. So the above equation you can see from this, that is this equation, we can see that if we move in the medium through x distance, which is equals to 1 by beta, then the amplitude it decreases by a factor e. Okay, traveling through this distance. When electromagnetic wave travels through x, which is 1 by beta, then amplitude reduces by e, and then we can, and 1 over beta is what distance? It is, we know beta, what is beta, so we can write inverse of that, and because beta is, see it here, this is my beta, inverse of this is 2 divided by mu omega sigma whole raised to the power 1 by 2, so 1 by beta is this. And this is what this is called penetration depth or skin depth. Means what? That if we have an electromagnetic wave, this is my conducting medium, and electromagnetic wave outside this conducting medium is having amplitude E component of electromagnetic wave. Amplitude is E naught outside, and when it will travel through this medium, that is conducting medium, amplitude will decrease, it will decay exponentially, exponential decay, and the distance up to which this E naught reduces to E naught divided by E, that is that distance in the conducting medium is the skin depth of electromagnetic wave in that medium. Okay, so this is how electromagnetic wave, when it propagates through conducting medium, it behaves. So it decays, there is exponential decay in its amplitude. Okay, so हम लोग इसको अभी इतना ही रखेंगे. We'll discuss more about this. And when we have pointing vector, we'll do this tomorrow because it is already 11. So this is about energy associated with electromagnetic wave. So how much? Because it carries, electromagnetic waves are important because they carry energy. Any wave, every जो भी wave होगा, that carries energy. So we are interested in finding how much energy it carries. So how electromagnetic with electromagnetic waves, how energy propagates. So how much energy propagates? To have that idea, if we have electromagnetic wave, it is incident on some area. So how much energy is absorbed by that area in some time delta t. So what energy is absorbed in delta t time, that idea we want to have. So for that we should have understanding of what is the energy carried by electromagnetic waves. And then we can predict this. So we'll do it tomorrow. If you have anything to ask, and today's lecture, mathematics part is there, and आपको ये mathematics part practice करना, you have to see because कुछ कुछ ऐसे steps होंगे जो आपको शायद confusing भी हो सकते हैं. You should ask about those. So I'm there to help you out and in right and doing those. So I'll be sharing this with you so that you can go through these steps. I have saved it as it is. You can see these steps or कुछ missing होगा तो you can talk to me. If you have anything to ask, any queries, you stay back, ask your queries, and rest of you can hang up.
Thank you, sir.
Okay.
Thank you, sir.
Okay.